All right. Now let's do question number 33. After doing question number 33, I will do 31. I just realized that I skipped 31. All right. Anyways, so cell X has an EMF of 2 volts and an internal resistance of 2. Okay. Cell has an EMF of 1.6 volts and internal resistance of 1.2 ohms. These two cells are connected to a resistance 0.8. Okay. Okay. What is the current in the cell X here? All right. It's a simple one. Okay. Since this is a positive plate, this is a positive plate, they are connected like this, so we need to subtract the overall EMF. So the overall EMF will be 2 minus 1.6, which is equals to 0.4 volts, right? Why I'm subtracting? Because both plates are facing each other. It should be positive towards negative and then positive, then it gets, you add up, okay? Anyway, so using the Kirchhoff's second law, what is Kirchhoff's second law? The total EMF in the loop is equal to the sum of potential differences, okay? So basically your 0.4 volts should be equals to your I, and what is the resistances? It is 2, 8, 1.2. So 2 plus 8 plus 1.2, which is actually equals to, I is equals to 0.4 over 10, 11.2, and it is equal to 0.10 amperes, which is A. So A is the correct answer. Okay? Alright. Let's do another one. Let me open the, I think it's this one. Yeah, we missed this question. Let's do this question first. And okay, let's start. A copper wire is to be replaced by an aluminium. Okay, a copper wire is to be replaced by an aluminium alloy wire of the same length, and resistance of copper has half the resistivity. Okay, so resistivity is what is difference. Copper has half, so it means that alloy has double the resistivity. Alright, what is the ratio? Diameter of the alloy wire and diameter of the copper wire. Okay. Okay, we know that the resistance of wire is actually equals to rho L over A. Okay, and the cross-sectional area is, you can say, if you take A over here, you can just write it as, if you are talking about copper, so let's label it like this. Yeah, this is the area. Since A is proportional to the diameter, yeah, the area is proportional to the diameter. If you write the formula like this, which is A is actually equals to pi d square over 4, which is r square actually. Okay, so A is actually equals to pi d square over 4, right? Or you can write it as d square, let's label it C also, of copper, okay, is also equals to 4 now I just plugged the area value here, and we can actually ignore pi because we are talking about the ratio, so eventually this pi and pi will cut each other in the end. So it's a constant, let's ignore it. Alright, so this is the diameter, and if you just remove the square, so the diameter of copper is actually equals to 2 under root rho Cl over R. This is what your diameter of copper is. Okay, now let's calculate the diameter for aluminium. I'll do it here. Okay, so the diameter of aluminium, again, let's see the resistance. Here they said that your resistivity is actually half, the copper is half, so it means that the resistivity of alloy is double. So can I write it as this? Of course I can write it like this. Okay, so now my area is actually equals to 2 rho Cl over R. Yeah, and my diameter of my aluminium, so So my diameter of my aluminium is actually, it will be equals to, since it is 4 multiplied by 2 is 8 rho Cl over R square. Actually, or you can just write it as that. If you are going to square it out, it will be 2 under root 2 rho C L over R and under root on this one as well. So now if you see the diameter of A and the diameter of C, so the only difference is under root 2, right? If I divide, in the question they are saying that alloy you need to keep up and this is to be kept down. So this part is going to get cancelled with this part, this 2 is going to get cancelled with this part, and only under root 2 will be left, and my dA over dC is actually under root 2. Okay? Okay, now let's do next question. This one, I think. Okay. Yeah, I think this one. Okay. Now, in this question, you should know that what is the sign for this one. This is what actually your LDR is. Okay, so let's see. In the circuit shown, a light-dependent resistor is connected to a 2 resistance, which is V1 and V2. Okay. Okay. And R1 is V1. Okay, the potential difference over here and over here is V2. The current in the circuit is I. All right. Which statement about this circuit is correct? Okay. Now let's see. So if you see the resistance of an LDR, it decreases as the light increases. Okay. So if I am getting more light, it has to, my resistance has to, if the resistance of an LDR decreases, it means that the light intensity is more. So if my resistance is decreasing, it means that my current should increase. Okay. So this is a wrong statement. They are saying that when your light intensity decreases. No. If my light intensity will decrease, my resistance will increase, and thus my current should decrease. So this is a wrong statement. The LDR is an ohmic conductor, not at all. It doesn't conduct like, it doesn't follow the straight line of Ohm's law. Its current and its voltage are not like behave linearly. So no, wrong. The potential difference V2 increases when the light intensity decreases. Okay, let's see. Since the current I decreases as the light intensity on your LDR, it decreases. Okay, so current will decrease as the light intensity is going to decrease, which causes the resistance of LDR to increase, right? So V2 is equals to IR2 will also decrease. Yeah, you getting the point? If my I2 decreased, yeah, I decreased, and it's saying that since I decreases, right? In this last part we also said when I decreases, it means that my LDR light intensity is also decreasing. Okay, if it's decreasing, my current is decreasing, it means that the potential difference across V2 will also decrease. Okay, so C is also incorrect. Now let's see, the ratio of V1 over V2 is independent of the light intensity. Okay, the ratio they are talking about. Okay, so let's say V1 over V2 is I1 R1 over I2 R2, where I and I are same in one loop, so they are going to cancel, so R1 over R2. So basically your light intensity, it's actually independent of light intensity, it's just dependent on the resistance now. Okay, so that's why there is the light intensity affects the current in the circuit, but the ratio does not depend on current. So that's why it is independent of light intensity. Okay, So option D is correct in this case. Okay? Alright, let's okay. Now let's solve this one. Okay. Okay. Now let's solve this one. A power supply and a solar cell are compared using the potentiometer circuit shown. Okay. The EMF produced by the solar cell is measured on the potentiometer here. Okay. The potentiometer wire PQ is 100 centimeters. This total is 100 centimeters. Has the resistivity of 5 ohms. Okay, in total. The power supply has an EMF of 2 volts and the solar cell has an EMF of 5 millivolts. Alright, which resistance R must be used so that the galvanometer reads 0 when PS is 40 centimeters? Okay. So, when your PS is 40 centimeters, right? So, the potential difference across the length of the wire, okay? So, the potential difference here, the or length of the wire PS, can I write it as your 2 volts, which is this, 2 volts and 0.4, because 40 centimeter in meters is 0.4, multiplied by 5 ohms and divided by R plus 5. Okay? So it's a potential divider. Since the total resistance of 1 meter is 5 ohms, you already know. The resistance at like 0.4, here it is also given that it's 0.4, but the total resistance of the circuit now you can calculate by extracting R out of it. Okay? But first you should know that a galvanometer is a very sensitive ammeter and it detects the electric current. Okay? So for the galvanometer to read 0, the EMF of the solar cell must be equal to that of the potential difference given above, which is 2. Okay? So when it is going to read 0, when the EMF of the solar cell is equal to that of the potential difference given, okay, such that the potential difference across the galvanometer will be 0. Okay? So actually by equating this potential difference to 5 millivolts, okay, which is the solar cell one, so you can extract R out of it. Let's do it here. So 5 into 10 raised to the power minus 3 is actually equals to 2 Now you keep on arranging this all, multiplying and dividing up, or let's do it. It is and 5 into 10 raised to power minus 3 into R plus 5. Okay, you keep on solving these two equations, alright, and let me solve it separately. Okay, so you just keep on solving this, like on calculator, just divide this by this, and then you will just subtract it. It's going to give 795, which is B. Okay.